Okay. So, this problem we have seen in the previous lecture, that there is a sudden drop in load by 16 megawatt. So, already we have solved this problem, but load drop means that what will happen, that speed will increase, that is frequency will increase, right. So, I will go to the what you call that next page. So, this already we have solved. So, this from this you have seen that your what you call that steady state, when you plot after solving this, when you have plotted for delta ft, that is steady state that is frequency deviation, that is showing steady state as positive, because load has your what you call decreased. If load increase, then the delta fss will become negative, right. This is your dynamic response. Another thing is, from here also directly you will get the what you call the steady state values from this what you call this from this equation, delta fs is equal to this much, right. So, next is your steady state analysis. So, from your figure 11, steady state error of frequency deviation can easily be obtained with u is equal to 0, right. So, this is done here, but I will go back to this figure 11, right. So, just hold on, I will go back to figure 11, this figure. So, this is our figure 11. So, from this block diagram, that I will go back to that, but from this block diagram we will go for your what you call the steady state error. Now, say that u is equal to 0, that is your, it is u is equal to 0 means that is your uncontrolled mode, right, u is equal to 0. Now, we will try to find out something like your steady state block diagram, when it is, of course, if that integrated term is associated with that like k upon s, then perhaps this technique is not possible, but in this case it is possible. So, and you know that t tends to infinity, right, that means s tends to 0, right. So, in this block diagram you put s is equal to 0, and for this case your delta f will be your delta f steady state. Similarly, for other values, this is delta p SSS, this is delta ESS, and this is your delta f SS steady state values, right. So, if we draw the steady state block diagram, right, so how it will look like, that means every block put s is equal to 0. So, in that case what we will do, right, I am redrawing for you. Suppose this is your 1 upon r, right, and this then 1 upon 1 plus STG is there. So, in that block you put 1, because s tends to 0, you put s is equal to 0, right. Then your what you call next one is your 1 upon 1 plus STT. So, there also you put s is equal to 0, it will be 1. Next 1 plus s square tr upon 1 plus str, put s is equal to 0. So, this also will become 1. Then this one your plus, this is your minus, this is delta PL, right, and here Kp upon 1 plus STP, put s is equal to 0 from that figure 11, then it will be simply Kp and output is delta F steady state, and it will be coming here, and this is your u is equal to 0, and this is actually delta ESS. This is your whatever the block has been splitted. So, delta PVSS, and this part is delta PGSS, and this is delta PL, the load, right. So, that means in that block you put s is equal to 0. So, this will be something like a steady state block diagram. That means feedback here is, if you this all are 1 1 1, that means equivalent, I mean if I make it like this. So, this is my this is u is equal to 0, right, and this is my minus and 1 upon r, right, and all 1 1 1. So, basically this is your delta PGSS. Intermediate things we are not considering, all 1 1 1, and this is plus, this is minus, then delta PL, and this is delta FSS, and this feedback is there, right. That means, if you and your delta PGSS steady state actually is equal to minus delta FSS upon R, because this delta FSS feedback is here, this feedback is here, right. That means this from here you can write, so delta PGSS means minus delta FSS upon R. So, we can write minus delta FSS upon R minus delta PL is equal to your delta FSS, is equal to delta FSS, right. That means, your delta FSS, right, and Kp was there, sorry, one here Kp was there. So, it is actually your into Kp is equal to your delta FSS, right, but Kp is equal to 1 upon d, right, Kp is equal to your Kp is equal to 1 upon d. So, substitute here Kp is equal to 1 upon d and cross multiply, then it will become d plus 1 upon r, then delta FSS is equal to minus delta PL, right. So, this thing is clear. So, I am clearing this and writing the final expression of delta FSS. So, delta FSS then is equal to minus delta PL divided by d plus 1 upon r. This is the steady state expression. I mean from the block diagram, if 1 upon s is not there anywhere, because you cannot put s is equal to 0 there, you just put s is equal to 0 and it will be a steady state block diagram, and you take any other problem also, it will give you the result, steady state values of all these things. And delta PGSS also we have seen, it is minus delta FSS upon R, right. Therefore, if you look into this one, suppose the actually for realistic system, the D actually we have seen, that is delta PL upon delta F, right. Now, if D is neglected, suppose D is actually very small compared to your 1 upon R, right. That means, your if D is neglected, suppose D is approximately 0, then delta F, the steady state value will be minus R into delta PL. This is the steady state error of the your what you call that the frequency deviation, right. So, this is your what you call that simply in one way to find out your steady state your what you call steady state error by simply putting that. Another is that final value theorem, right. So, this is in, so therefore, in this diagram we put simply s is equal to 0, right, and from that we got the or what you call we got the steady state error. So, we will go back to this that steady state that the next page, right. So, this is what I showed there, that delta minus delta FSSR minus delta PL into Kp is equal to this one. So, this is actually delta F steady state is equal to minus your delta PL upon d plus 1 upon r, right. So, this is equation 18. So, this is the steady state error of the frequency. Next is that composite frequency response characteristic. So, now one thing I would like to tell, that when we write down the equation that delta Pg minus delta PL is equal to 2 Ah upon your F0 into ddt of delta F plus dPdu, right. So, when you if you look into that equation, I will go back to that before moving to that, right. So, just hold on, I will go back to that, right, just hold on. So, when we are going for your power balance equation, this equation, that this equation when you go, right, this power balance equation when you go this one, I mean simply if you go to this, then another point is that we assume that load is your what you call it is sensitive to the changes in frequency. Now, at steady state this term will be 0, d dt upon delta f will be 0, right, and this is my delta PGU, P per unit PU. So, understandable that it is per unit. So, I will write delta PG minus delta PL also per unit is equal to at steady state. So, I can write this is steady state and this is load delta PL, right, and steady state this term is 0, means this is 0 is equal to d into delta f SS, right. So, so this is your what you call delta PGSS my minus delta PL, that means my delta PGSS is equal to delta PL plus d into delta FSS, right. This we know. Therefore, two versions are there. One is delta F, your what you call delta PGSS, we know that delta PGSS is equal to minus delta FSS upon your R, right. But this delta FSS, we know that here I am writing for you that delta PGSS steady state value is equal to delta PL is there and d plus d into delta FSS is equal to, we have seen minus overwriting it divided by d plus your 1 upon R, right. This is your, that means that delta PL will be there minus your what you call d into delta PL divided by d plus 1 upon R. So, in that case what is happening, that if you look into this term, if you take your what you call delta PL and delta PL common, then here I am writing delta PGSS, I am making it on it, but you do it on that notebook, right. Delta PGSS will be equal to, take delta PL common, then it will be d plus 1 upon R this side minus d, right, divided by d plus 1 upon R. So, d will be cancelled and finally, this one can be your what you call written as delta PL, right, your divided by your into your d, your here it is 1 upon R. So, basically it can be written as 1 plus your what you call R d, right, because it is 1 upon R multiply. So, it will be R d plus 1. So, delta PGSS will be delta PL upon 1 plus R d. That means, this R d is greater than 0, that means 1 plus R d is greater than 1, that means at steady state, although generation should change the load. So, at steady state I am just rewriting this, first let me clear it, I am just rewriting that expression. So, delta PGSS is equal to delta PL divided by 1 plus R d, right. Although R into d actually for realistic parameter is quite small compared to 1, but anyway it is greater than 1. That means, delta PGSS if d is approximately 0, then at steady state delta PGSS will be equal to delta PL, right. But in this case it will be less than delta PL, because it is greater than 1. So, it will be less than actually for uncontrolled mode. So, your what you call generation will never match exactly to delta PL, it will be very less, maybe 1%, 2%, not more than that, because the load is sensitive to the frequency deviation. That is why this term has come, right. If you simulate it, you can easily verify this, right. So, we will go back to your what you call that to that composite characteristic, right. So, just hold on. So, that means your this I explained. So, also delta PGSS is explained. Now, composite frequency response characteristic. Fourth figure, first let me go to the figure, then so composite frequency, just hold on, let me reduce this thing such that whole thing will come together. So, just hold on. So, this figure, that is, suppose you have it is isolated system only, suppose you have n number of generating units and they are all, I mean, and all non-reheat turbine I have considered here, you can consider reheat also, no problem, but all are non-reheat type. So, and you have n number of units. So, in that case what will happen, that this is governor for unit 1, this is your governor for unit 1, governor for unit 2, and this is say in general that nth governor. This is the your what you call, this is, and this is the your turbine transfer function, because it is non-reheat type, only one block 1 upon 1 plus STT, that we have seen in the previous classes. So, now for each generating unit, generating power delta Pg1, delta Pg2 up to delta Pgn, right, and all these things can be represented by a single your power system, your time, your block diagram, that is Kp upon 1 plus STP, because all these generating units they operate in parallel. Therefore, you can find out their equivalent inertia H, and from that you can represent it by a single block diagram. So, no need to consider that separate block diagram for your separate unit, because we will assume all the units, right, they are in coherent group, they swing in unison, that means their increase or decrease speed will remain same. So, that means this part you can represent it by a single transfer function, right. And if you look into that feedback, then this is your delta F. So, it has gone to for unit 1 1 upon R1, for here it has come 1 upon R2. Similarly, for nth unit it is 1 upon Rn, right. And this side supplementary or integral controller is there, that we will see later, that is U11 for unit 1, U22 and UNN, right. So, in this case also if you want to find out the steady state values, then at steady state I told you when S tends to when t tends to infinity, S tends to 0. So, in this block you can put all S is equal to 0, that means this term should not be there, it will be 1, it will be 1, it is 1 1 1 1, and this will be only Kp, right. So, after that it will be a simple steady state block diagram. Of course, U1 is equal to U11 0, U22 0 and UNN 0, right. So, from that you can find out, and this is delta F SS, easily you can find out the steady state values. So, this is your what you call in that composite your multi unit isolated power system. So, many units are there and this is isolated, that means not interconnected with any other your power system, right. Now, we will go to your that your derivation, right. So, now if you go back to this, so I explain everything. It may be one thing is there, that your what you call, this is nothing, right. So, it may be assumed that all the generators that I told you swing in unison, and the equivalent generator has an inertia constant equal to the sum of the inertia constant of all the generating units, I told you. So, from figure 14, that is the figure 14 I so explained, steady state error of frequency deviation can be given as, right. So, same way you can find it out. So, you can write delta FSS is equal to minus delta PL upon D plus 1 upon R1 plus 1 upon R2 up to 1 upon Rn summation, right. Or we can write delta F steady state is equal to minus delta PL divided by D plus 1 upon Req, where Req is equal to 1 upon R1 plus 1 upon R2 plus 1 upon Rn. In general sometimes we write 1 upon, right, sigma I is equal to 1 to n 1 upon Ri, right. Sometimes we write this way. So, this is your what you call, this is your that your equivalent this thing, and this diagram already explained, right. Now, already we have discussed in the previous section that the supplementary generation control action, right, is much slower than the primary speed control action, that we have discussed. As such, it comes into action after the primary speed control has stabilized the system frequency, right. When actually primary your control is quite fast acting, right, compared to the your slower supplementary control action, right. So, primary speed control has stabilized the system frequency, then supplementary control comes into action. For isolated system, the function of AGC only to restore the system frequency, because it is not interconnected with any power system. So, that power flowing through that your connected line, that is we call tie line, is not coming in this picture, right. It is only isolated system to the specified nominal value, and this is accomplished by adding a reset or integral control. So, this is actually integral control. So, what happens, this is a composite system, delta f, that is integral controller, minus k I upon s, then output is u, this output is u, right, and then this fraction of that one a1, a2, an, it has gone to this, right. So, a1 plus a2 plus a3 plus up to an, this is equal to 1.0, right. Now, actually in steady state, this is delta f input is given to the controller, but at steady state you will see that u steady state actually is equal to delta Pg steady state, right. I mean it is something power increase, or what you call power increase, suppose load demand has increased. So, u steady state, and that is actually is equal to delta PL, the total load, right. Because when you consider steam hydro turbine or your steam turbine, thermal power plant or hydro power plant, for if load demand increases, say, then you have to give more input to the your what you call this your to the steam turbine, right. And for in the case of hydro turbine, that hydro power plant, that you have to open the water gate, right. So, that equivalent whatever is come for steam or water, that is nothing but equivalent to that, I mean power, considering lossless, that power generated. So, actually at steady state you will find USS is equal to delta PSS is equal to delta PL, right. So, that means you suppose you have n number of units and you have to give this fraction, that which generator will generate how much. For example, suppose my load demand has increased to 100 megawatt, right. Suppose I have 3 generating units, right. I have 3 generating units. Now, that this will not consider in this course, right, but here that economic load dispatch comes, because suppose this 100 megawatt you will your what you call, you distribute among these 3 generators such that your fuel cost will be minimum, right. For example, suppose if for this case if A1 comes 0.25, say A2 comes 0.3, then A3 will be 0.45, right. That means your what you call that means at steady state that U11, I mean at steady state only U11, I can put it like this, U11, that steady state will be your A1 into U, right, and that is my that I told you that U steady state will be delta PGSS will be is equal to PL is equal delta PL is equal to say 100 megawatt load. Suppose I am considering instead of small thing, suppose I consider that 100 megawatt for your understanding, then this USS will be actually 25 megawatt, right. Similarly, this steady state value of U22 will be also will be 30 megawatt, right, and this U33, right, U33, because we have taken 3 units, suppose n is equal to 3, it will be your 45 megawatt, right. So, that means this at steady state that generating unit 1 will generate 25 megawatt, the 2 will generate 30 megawatt, and the unit 3 will generate 40 megawatt, but that will not consider here, right. So, that means that A1 plus A2 up to summation of all A, this is called actually that participation factor, right. So, A1 plus A2, that is the meaning for this one, right. Now, another thing is, so this is already given. So, that is why delta Pg whatever I said, because here delta Pg1 SS actually it is nothing but U1 SS, same thing you will get. This will be also U11 rather U22 SS, and this will be actually UNN SS, all steady state values. So, that is why delta Pg1 steady state will be A1 into delta PL, A2 into delta PL for delta Pg2 SS, and similarly for delta PGNS it will delta PGNSS it will be AN into delta PGL, right. Actually something is written, the readers may easily verify to the computer simulation, you can check it in MATLAB, you can easily check it, right. Data, another thing I did not mention yet, later I will tell you, right. So, another point is that just hold on. Another point is that your regarding that integral control action. First we will see isolated area, because in this note it is not there. So, I will write, first I will draw it here, right, the block diagram only for non-reheat type turbine, such that our analysis will be easier, non-reheat type turbine, and the rest if you understand this, it can be applicable to other system also. So, if we draw the block diagram, I am making it somewhere here. If you draw the block diagram, this is minus 1 upon r, right, and this is 1 upon 1 plus S T G, this is 1 upon 1 plus S T T, and this is your delta P G, this part, this is minus delta P L, and this is K P by 1 plus S T P. Just I hope it is understandable. It is 1 plus S T P denominator, and numerator is K P, and this part is delta F, right, and this block is completed, right. So, and this is actually you have one integral controller, that is your minus K I by S, and its feedback is, that is your frequency, this is frequency. So, input is the frequency, right. So, in this case what we have to do is that regarding optimization we have not talked about. So, for isolated system we talked about something on optimization, right. So, this is my delta P G, and this is your delta P V, right, delta X C, this variable is actually delta X C, this is non-reheat turbine, and this is output U, right, but output U will consider now as a state variable, because our objective is to find out the optimal value of K I, right. How we will do it? There are many ways. So, this state variable, this one is x 1, this one is x 2, right, this one is x 3, and instead of u, because output of integral controller is u, but we will treat this one as your x 4. So, 4 state variables are there, right. So, 4 state variables are there. So, from that we will find out x 1 dot, x 3 dot, x 4 dot, x 3 dot and x 4 dot, right, and how to optimize K I using that concept of degree of stability. Thank you very much. We will be back again.